Modular Tech Talks is an exclusive series featuring internal presentations from our engineering team explaining the inner workings of the modular technology stack. In this edition, Andrew Luau explores the unique architecture of the graph compiler and how we address the challenges of expressing high-performance computation on a variety of hardware, all while maintaining control over execution and delivering an exceptional user experience.
Okay. All right, let's go and get started. So this is the second of our modular tech stack bottom to top series. Last time we talked about the kernels and Mojo. Andrew from the graph execution team is going to talk to us about how we execute an ML graph in Modular. So take it away, Andrew.
Yeah, so we have a lot of slides, so thanks for coming, guys. I'll try to make this understandable, but also quick. So the part of the stack that we are going to be talking about today, as Josh mentioned, really has to do with dealing with graphs. And what does that mean? Well, graphs are essentially these high-level kind of ML programs that are super popular. They represent something like Llama or DeepSeek. The graph execution part of the stack is really concerned with running like a single iteration of these models, because of course, in these days, LLMs, they usually require multiple calls to this notion of a graph in order to, get a final output. For example, one call to a graph generates a single token. You want to generate a lot of tokens, right? So it turns out that this is actually a pretty big part of the software stack. So there's going to be a lot of sort of disparate pieces of software that we're going to be talking about today. The one thing that I want to sort of use as a theme, as design considerations throughout this entire stack, are these idea of having good performance when you run these graphs, having good control over what exactly is being executed, all while having like a good user experience. And these are actually, if you think about it, really themes in the entire company, so shouldn't come as a surprise. But as I alluded to, we're really talking about three separate pieces of hardware and our software. And the way I would describe it is we have some pieces of software which are used to define a model. We have another piece of software which optimizes and then compiles the model. And then, of course, we have this runtime at the end, which actually runs the model in a nice performant manner. And I'm going to be talking about the stuff in green today. Of course, the thing that is sort of being left out is how we deal with third-party frameworks like PyTorch. And we're really good friends with them, but we're not going to be talking about today. Maybe in the future, we can have a future talk about PyTorch. So though nominally, we're going to be talking about these three separate pieces of software out there, they are sort of all connected by their shared usage of certain MLIR dialects. So what I've done here is I've listed out kind of the 5 major dialects within our graph execution stack and highlighted, which dialects are used by which specific pieces of software. So the way I'm going to approach this sort of talk and this sort of deep dive of the entire stack is we're just going to start from the top and go down. So at the start, we're going to be talking about the dialects of RMO and Mo, which are used by both the Graph API and Graph Compiler and co-designed. So let's first talk about what the Graph API piece of software is really trying to do. While at a high level, you're just trying to create an experience like TensorFlow or JAX, a Pythonic way to define these ML models. To go a little bit further, if we imagine, to draw an analogy with Mojo, Mojo is really just this convenient way to sugar the generation of MLIR, namely the lit and kgen dialects. Well, the Graph API is just a really nice way to sugar the generation of these RMO and Mo dialects. What it looks like is something you see on the screen over here. It's very Pythonic, and maybe it looks similar to what you might find in like a PyTorch model or a JAX model. So one major thing to call out as a key design principle of the whole entire Graph API is that it is fundamentally a static computational graph builder. This is in contrast to other ML frameworks like PyTorch, which are more eagerly executed and how they generate quote unquote a computational graph. And the main reason why this choice was made is all about performance, right? Which is one of our first themes. We are fundamentally, you can think of us as like a compiler company. In order to compile something, you need like a static thing to work with. So that is pretty important for doing like these things to get good performance and run optimizations like memory planning. Of course, the downside is the UX is a little bit wonkier because you are dealing with another layer of indirection inside of the graph builder, since you're not directly executing code immediately when you build that IR. So this sort of highlights a set of tension between the Graph API and the Graph Compiler, which I want to talk about, where the Graph API really wants to make it really easy and give the user a lot of control over building their ML models and making it very precise about exactly what you are going to be executing in the future. Meanwhile, the Graph Compiler really just cares about performance, right? So this leads to like some tension between them, which we'll discuss. And what I've done in this set of slides is I've also listed some key considerations for both the Graph API and Graph Compiler. The first one I'll talk about is this idea of symbolic shape system, which is a pretty important part of both the Graph API and the Graph Compiler. So the way I'll talk about this is I'll get on my soapbox and just say that previous generations of ML frameworks and compilers maybe did not have the best support for dynamically shaped tensors within their stacks. For example, it was very common in older frameworks and earlier generations to represent values which were dependent on runtime as sort of these question marks. And this is fine as a hack, but the problem, of course, with the question mark is it really is this sort of poison value that you cannot, do anything with. By being poison, I mean that once you have a question mark, it tends to just propagate other question marks. And eventually your entire computational graph is full of these question marks and you know nothing about shape, about the shape of your data. And that's like really, really not useful for like a compiler-based approach. So the good thing is we don't take that approach with dynamic runtime shapes. Instead, we have the symbolic dimension system within our compiler where we represent unknown or runtime dependent dimensions with like a variable like A or B or C, right? And the cool thing about this is that it allows this very natural representation where you can then compose some of these variables together to represent like output shapes and stuff. So what you have here in this lower right-hand example is you're concatenating two tensors, which are completely runtime shape dependent. And instead of getting a question mark, you actually get another expression. So the basis of this representation allows you to build like a bunch of infrastructure, which we'll call broadly shape inference. And basically, it's all about like simplifying some of these symbolic dimensions down into a simpler form, right? So, and I'll just say it, our shape inference pipelines are really, really good right now. That sort of analysis is really, really solid. And 99.9% of the time, we can usually take a really complicated graph coming from who knows where and simplify it down all the way to its like simplest form. It's also important to call out that though the symbolic shape system does give us a lot in terms of like removing question marks, it does like sort of permeate throughout the entire stack. Because now you need to deal with it in the Graph API, you have to deal with it in the Graph Compiler, you have to deal with it in the runtime, so on and so forth. So it does add, again, more complication. But that complication is well worth it because knowing these facts about shape is just really important for all of these different optimizations that we have out there, like memory planning, scheduling, kernel specialization, et cetera, et cetera. One other sort of benefit it gives us on the Graph API side is actually an improvement in UX. And the reason for this is the Graph API takes this graph building kind of approach instead of eager execution. What this basically means is that it is very easy to create IR, which might not shape check actually at runtime. And that's bad because it makes the identification of invalid programs dependent on actually running the thing with regards to shape. So the good thing is like all our shape inference pipeline logic is sort of modular, name drop. And this allows us to basically push a lot of shape inference, local shape inference at least, to the Graph API. So when you construct certain operators, you can usually do this forward shape inference really easily. And this allows us to catch a lot of possible shape errors and incompatibilities at build time instead of runtime. Okay. So that's all about the shape system. The next piece of tension between the Graph Compiler and the Graph API is the fact that the Graph API really wants a rich operator set to deal with, and the Graph Compiler really doesn't. And I'll explain this in the next few slides. So Mo actually came first. Like the Graph API and RML came later. So the history of the company is we knew we wanted to build up this Graph Compiler. We wanted to make it really performant at optimizing all these like third-party ML models out there. So one of the key design principles that we did in order to guarantee good performance in the Graph Compiler is we want to make it like easy to build these sort of optimizing passes at the graph level. And the key parts to this about creating these optimizing passes easy is, one, you want to make it easy to guarantee your transformations are correct when you write these optimizing passes. And two, you want to make it like relatively easy to write these passes, right? So, and this led to sort of these principles of the Mo dialect of, one, we wanted like really strict shape semantics. And two, we wanted kind of like this reduced operator set where we didn't want our operators to do much, for example, auto broadcast, because that makes it complicated to write other passes, as well as having a limited set of operators which compose well in order to do the things we wanted. Tyler, you have a question.
I was wondering if you could go back a slide. So this is awesome. Thanks for doing this talk. The example here is just straight PyTorch, right? This is not the example given. This nothing to do with us. Okay, so I was, but you're just saying like we have a similar functionality essentially.
Exactly. But the difference, of course, is Torch is eagerly executed. So you're actually like running the code and getting the error. The thing is, we are actually building a computational graph, and we're able to catch really, really early. We were able to get the same experience without actually running the thing, running like the addition kernel.
Yeah. Okay. All right. So I wanted to understand that last bullet, what you were trying to say there. You're saying that it's easier for PyTorch than it is for us, but we can do it anyway.
Exactly.
Yeah. Okay. All right. Yeah. That makes sense.
Okay. So back to this slide. So basically, we want our operator set in the graph compiler to be, not a lot of operators. We don't want 2,000 PyTorch operators to deal with, because each one you have to deal with in a pass. It's just a lot of permutation. And we want the operators, the IR at this level, to be really strict. Like if you generate something that could potentially be wrong at runtime, you immediately say it's an error, right? And the other thing to notice that like all of these are sort of principles, not dogma. There's like several exceptions, but this is the reality of the graph compiler. Okay, so basically the way I would say it is that the graph compiler, the Mo dialect in the graph compiler is really an optimizing graph level dialect. That's the point of the slide. But the fact that it's an optimizing dialect means it's actually really, really hard and cumbersome if you're thinking on the level of like the graph API to construct certain types of operations directly in Mo. For example, in this slide over here, what we have on the left-hand side is just the simple Torch program like before, where we're doing an addition. And the thing about this addition, it's broadcasting addition, so there's a little bit of fanciness. Well, the corresponding IR on the right, in order to express this similar idea in the graph compiler, is as shown. And basically, it's really like 6 pieces of IR. And there's actually like pretty complicated manipulations of the shape system that you just have to know in order to make this work out, right? So if you are the graph API, you really don't want to manually create all of these operations on the right just to do the simple addition, right? That's sort of the point of the slide. And remember, you have to make MLIR because the graph API just should grow for MLIR, right? Tyler.
Can you go back a slide again?
Yeah.
I was interested in the graph with the number of PyTorch jobs.
Yeah.
This is fascinating. This is not only a gigantic number of PyTorch jobs, but it's still to this day going hockey stick up. But like, is PyTorch ops versus Mo actually the right comparison here? Because wouldn't, for example, our Mo be at least closer to apples?
Yeah, that would be closer to apples and apples. But the point is, you don't want. So the reason why PyTorch has a lot of operator sets is because it's fundamentally trying to have a different experience. It's not being built first as an optimizing dialect, right? So it's fine to have 2,000 operators, but the point of this slide is to say for a compiler, you don't want to have 2,000 operators you have to handle.
Yeah, that makes sense. I understand it's a little bit orthogonal to your point, but it makes me curious. How many RO ops do we have right now?
I don't know that number. Yeah, maybe someone else. I would say it's probably under 200. So not much.
Yeah, it's similar order of magnitude to our MOOPs. We don't, in fact, like there's cases where we have fewer our MOOPs than MOOPs because, for instance, we don't need a broadcast op in Armo because the ops are broadcasting. There's multiple matmul ops in Mo, and we only have one in Armo, and it like lowers to one of the two in Mo. So it's like similar order of magnitude. We're not routinely adding a bunch of Armo ops on top.
Yeah, not yet, but I think the point is that why is PyTorch operator count increasing like this? It's, people want to do stuff, right? And if it eventually becomes useful for people to add those ops, blocking ops.
I want to. I think if you dig into and what these ops actually are, a lot of them are manual fusions.
I see.
And they're also implementations depending on there are multiple implementations depending on the layout of the tensor. So I think like one of the huge values of our stack is actually that because we have automatic fusion and because we have the ability to reason about layouts, although this is the layout thing in particular is something that PyTorch is improving. But a lot of the historical ops are because of like layouts and things like that. We're able to implement a much smaller operator set, which makes it a lot easier for us to bring up new hardware targets, basically.
Makes sense. Eric?
Yeah, related to this. So I know that when you have a big operator set and you have to lower to a smaller like RISC style set, sometimes you have to expand operators into multiple Mo ops.
Yep.
But then, like we were saying, the reason some of these exist is because by fusing them together and having one big complicated op, you can define a custom kernel that's faster.
Yeah.
So do we ever get to that problem where you've expanded it so much that now you don't recognize the original pattern and you can't fuse it down to something? Or how do we handle that problem?
We can talk a little bit more about fusion later, but this thing where you want to manually fuse ops is definitely something that happens in our stack, and it's sort of covered by the custom operator use case. So yeah, that's sort of my answer there.
Okay.
And then Wei, I believe you had your hand up. It's no longer up.
Oh no, I just want to say like the PyTorch has thousands of op. It's not like that. Their core op is in the range of like 100 to 100 to 200. And the thousands is just because they have variations, like vector plus tensor is one thing. Like you may see 10 add up, but it's basically just add, and they have different kind of like a broadcasting semantics to add it. So the core op is probably in the same order of magnitude as Mo is.
Yep, makes sense.
Yep.
And Brian asked how many Mo ops are there. There's like under 100 right now. Okay. Where am I? Anyway, the point of this is, of course, this thing that has been alluded to in the chat, where how do we deal with this the problem that you want an optimizing dialect, you want to potentially a lot of variation, whatever crazy ML engineers want. Well, the solution is like you make this higher level dialect, which is RISC or is more complicated, allows more complicated semantics, and it lowers into your optimizing dialect. So that covers like the RISC versus CISC part. The other part of discussion is how do we deal with the strict shape semantics? Well, the answer is we can rely on the shape inference system, that infrastructure that I described previously, and basically insert like symbolic shape conversion checks in this transition between CISC to RISC, and depend on the shape inference passes to like clean it up, which as I said, they're very good, so they almost always clean them up. So here's an example of that. You have one line in the graph API, expands to a lot of Mo, and then that gets simplified by the shape system down to just like a single operator. Okay, so that's about kind of this tension between operator sets, between the graph compiler and the graph API. The other thing to highlight about the graph API is we actually don't want to make it impossible to represent certain types of programs. And here I'll get on my soapbox and talk a little bit about maybe some of the problems with maybe the first generation of ML frameworks or compilers in the past. And that is they tended to want very, very little dynamism at all, not just dynamic shape, but things like control flow were limited and side affecting operations, the representation of those or support for those were relatively poor. But if we think about what won ML these days, it's like LLMs, right? And LLMs by nature are inherently dynamic. People do all sorts of crazy things with them. Like these routing networks that you see down here. And the reason for this is probably like one of the reasons why PyTorch is so popular, because it's like very easy and natural to express these types of programs within this framework. So we want to have like sort of a similar experience, or have this as a similar design constraint, where we want to make sure the user has control over these aspects, which are necessarily to give the performance that they need. So I won't get into the details super strongly, but basically we support, side effects and control flow within the Mo dialect. And then we also support similar sort of sugar on top of those in the Graph API. These things are at various stages of development, but the infrastructure has been laid out to do them. And it's important to note this because even some modern day frameworks like JAX don't fully support like mutation or dynamic shape even to this day. And what does it look like in Mo? Because I'm not really going to go into the details too much, but the top program represents what like our representation of control flow, and the bottom, how we implement things like side effects and mutation. Okay, and then to move it along, the final thing I want to talk about is this fact that we easily allow the definition of custom operators within the Graph API. And this sort of acts as like a sort of an escape hatch to all of the design decisions I talked about previously. So I won't belabor this point too much because I feel like it has a lot of discussion already within like throughout the entire company. It's known as like the extensibility API or whatever. We put a lot of work into it. And if you're more curious about how exactly one creates like a custom operator and uses it within Graph API, you can look at the set of tutorials from Brad and company. Why would a person want to create their own custom operators? Well, really, it's all about giving the user full control over what's being executed in the graph, right? And this goes to this general theme in the company about control, where sometimes we don't want to depend on magic compiler passes to get full performance or whatever thing we want. And the clearest example of that within our stack is Fusion, where there are very complicated forms of Fusion out there, like you see in Flash Attention, which the compiler is just not in a place where we can automatically do that. But we don't want to like block or be dogmatic about it. We want to still give a user a way in order to get full performance, and custom ops are sort of like the solution to that. Okay, so in conclusion, the way I would describe the Graph API wants to have good representations, which can model all sorts of programs that we want to model, like mainly LLMs these days. And the Graph compiler wants to optimize all of these things. And the main kind of thing is that you have this like RMO dialect, which lowers to Mo, and you can have this progressive lowering to support all these semantics that you absolutely want. Okay, so that's the sort of front end part of the stack, the Graph API. The next part of the stack has to do entirely with the Graph compiler, but it also has significant interactions with the Mojo programming language, because again, Mojo is pretty pervasive throughout our entire stack. Okay, so here, the way I'll frame this is as a current strategy for the Graph compiler. A major design decision is that most of the code we actually generate to run at runtime is JITted at compile time. So it's not like we are calling into prepackaged, libraries. We literally generate the code that is used to run the model when you give us the model into the Graph compiler. And this is certainly a decision. Why is it like particularly useful? Well, a lot of it has to do with like performance for sure, because you want to be able to, for example, specialize your kernels for specific shapes. Whereas if you ship like, a library, that becomes really cumbersome and difficult. There are a lot of bad trade-offs you would have to make in order to make that happen. And we also want to deal with this thing called operator fusion, which Eric has alluded to, and I'll talk a little bit more later. The other benefit is that you're basically only compiling for what you exactly need too. So theoretically, you're also having these compile time improvements potentially, depending on how crazy you go with the specialization and fusion. So therefore, by JITting everything, you kind of get both performance from specializing kernels, as well as a little bit of user experience from lower binary sizes and compile times. Now, of course, because you're jitting everything, compile time is like a key challenge because you can never amortize that cost, right? Versus something like where you call into a prepackaged library, the cost of building that library has been amortized over all the times you are potentially calling it, right? There's also just like a lot more infrastructure and work that needs to be done to support something like this, which we'll talk a little bit about. And then the final key challenge I'll talk about will make more sense when we talk about Fusion, but it essentially has to do with how do you like balance the control the user has with writing a kernel versus the fact that the graph compiler or some metaprogramming layer wants to mess with it. Well, first off, I saw talking about like the idea behind specialization, and this is just like really, really simple. If you just draw the analogy to Mojo, what does it mean? Well, quite literally, within the kernel library, we have methods which have parameters in them, such as, in this case, we have the convolution operator is parameterized on static strides. Presumably, it's parameterized on static strides because there's some optimization in the kernel that can use this information to make like a better kernel, right? It only makes sense, or you only have the information of what the static strides for what any particular tensor is in the graph compiler, right? Because you only know the strides once you have an actual computational graph with tensors that call into a conv. So this is why like this sort of layer makes sense in the graph compiler. You can't specialize without knowing your workload, essentially. And you only know your workload once you have the graph. And sort of the analogy here I'll draw is that then it's up to the graph compiler to like properly instantiate the concrete function that can be used. So in this case, you might have in your graph, this convolution with these particular sets of shape, and then it's basically the job of the graph compiler to then initiate this kernel with the proper static strides and static dilations and all of these other fields. So that one's a simple one. The more complicated one is this idea of operator fusion. I won't go too much into detail here because it's just like a lot of other stuff. But the way to think of it is operator fusion is not really one thing. Instead, it's sort of this family of optimizations out there. And the one connection that makes all of these separate optimizations sort of a family is that it involves taking disparate operators, which are next to each other within a computational graph, and then combining them together. And the idea is by combining them together, you can do it in some way, and it's sort of dependent on, again, the type of optimizations. It's a family of optimizations. But by somehow combining them together, you can generate a better kernel, which is more performant in some manner. But again, this only makes sense to do in the graph compiler, because at that point in time, you actually know your workload and you know which operators are next to each other. The other difficulty with doing this fusion is we do want to basically use Mojo to create all our kernels, but then we sort of want to compose them, right, in order to implement these things like fusion. And that's a sort of difficult, interesting like set of trade-offs, because you have to constrain the way people write kernels in Mojo in order to make it feasible for some other layer to then manipulate these and compose them together, right? So we'll talk about what that looks like, but this is a challenge which has a lot of trade-offs in both performance, control, and UX. But the way we kind of unify this sort of idea is that fusion is almost always implemented within the modular stack through these lambda functions. So the idea is that you can pass these other functions as parameters to kernels, and by passing in the right lambda fusion, you can sort of implement like a large family of optimizations of fusion that I described in the previous slide. So what this does is it really just changes to the problem of how do kernels compose together to create fusion to one that is just simply, it's the exact same problem as specialization. Instantiate the right parameter and you get the right thing. Okay. And then we also have all sorts of random other parameters that we specialize for that are not like tied to any particular aspect of the computational graph, really. Like these are things like, the target, which is sort of passed in as like an option. Tracing is also sort of handled in this way because we need to generate like traces for profiling and stuff like this. And there's also just like a bunch of random stuff. That's kind of what I'm saying. And all the stuff I sort of described is what we call like the kernel API, how you are supposed to write kernels in specific ways in order to like have a form that the graph compiler can manipulate and instantiate these right parameters. So everything I described about the problems of specialization, fusion, all these other random parameters, they're just really about like instantiating the right parameters, which is how you do metaprogramming in Mojo. So it really shouldn't be something super special or difficult. And what layer does this sort of proper instantiation of the kernels and handles all of this logic? Well, we call it MOG, which stands for Modular Graph Generators. Okay, and here's basically some characteristics of what MOG kernels look like, or the MOG dialect look like. They're composed of these like things called MOG.kernels. So the interesting thing to note here is that at the high level, there's still data flow value semantics. So they're very similar to kind of like the Mo or RMO operators we described previously. The main difference is now the body region. We have these body regions, which sort of represent like the implementation of these operators. Internally over there, they describe imperative execution. So the main idea is that within this body region, you have something that represents like how the kernel is implemented. And then you have a set of transformations that can then optimize these regions and implement things like fusion or specialization or dealing with these magic parameters we described previously. It's also important to note that right now, everything is written in kgen. And that is probably like not the best choice. Kgen, for those of you who are unaware, is kind of this like lower level dialect, which is used inside of the Mojo language. So right now we do all of these like kgen to kgen dialect transformations in order to implement all of the features I described in the previous slides. And this is actually a major challenge because kgen, like Mo, is an optimizing dialect, except it's like even worse because, you know, this is what it looks like for a single kernel. And this is something that is actively being changed, but it is the current state of the implementation right now. So in the future, this is sort of like kind of active work, but we're trying to get away from the system because it does slow us down and it does make it difficult to do a lot of the things we potentially want to do in the future. So in the future, for example, instead of doing kind of these Mojo dialect to Mojo dialect transformations, our approach is to create like this higher level generator dialect, which then generates something in the Mojo stack. So whether that be kgen lit or like Mojo plaintext. And right now, I think the winds are shifting in that we're settling on creating plaintext Mojo, right? Where this generator dialect does some logic about handling the fusion, about doing the logic of how the kernels JIT for our graph will look like, and then it will generate actual plaintext Mojo, which is fully compiled. And we hope that this will result in like something that is both easier for the graph compiler team to maintain, but also gives better UX and control because you can quite literally see what kernels the graph compiler is generating. Though there are other challenges around compile time that we have to manage here. Okay, so if there's anything you should get out of this section is that once you have a computational graph, you want to do all these things like specialization and fusion. And therefore, this requires basically the graph compiler to be this metaprogramming Mojo machine at the triple M. There's a lot of work that can be done to improve the current experience, but right now it's there and it kind of like all works. Finally, we have this thing called the kernel API, where we actually have to constrain the way people write kernels a little bit in order to make it compatible with all the systems that we just described. Okay, so that kind of covers the MOG dialect and the middle layers of the graph compiler. The final bit of discussion will be about the runtime. And Eric is here, which is great because this is the part of the stack which I actually have the least amount of experience with, but I can talk a little bit about some of the, at least the high level design points about this. And Eric can correct me if I say anything wrong.
And no one can correct me if I say anything wrong.
Yeah, and Eric is like the man, you know, so maybe
I might be wrong, but no one will know well enough to correct me. So
yeah, exactly. Ivan might is the other like runtime guy, so maybe he knows something, but I don't think he's here right now. But anyway, at this point of the stack, we've defined our model, we've compiled our model into something with like a bunch of JITted kernel code, essentially. And now we need to somehow run the thing, like call all our JITted functions in the proper order in a performant way. And this is kind of the challenges the runtime is trying to solve. Doing this in a performant manner. Once you're down to this layer, you're also buffer semantic. So you have to deal with buffers and do memory planning and manage potentially external data and stuff like that. And you also, because you want good performance, you have to expose parallelism, concurrency, and make sure like the entire stack runs on all the pieces of hardware that you potentially want to run it on. So like different CPUs, different GPUs, et cetera, et cetera. So let's talk a little bit about some of the history or current design points about the runtime layer with regards to this idea of efficient execution. And by the way, the thing that actually runs things is called the GraphRT, and it's basically our graph executor, and it's built on async RT, which is our concurrency and threading library. So one interesting thing about the GraphRT, which is the name of the actual runtime, is it's a runtime with data flow semantics, which I thought was actually like kind of interesting. What does this mean to people who are not aware? Well, basically, semantically, the execution order is merely constrained by data dependencies, but it's not necessarily like fully defined the exact ordering in which certain functions are going to be operated on. So this means that if you have this graph on the left-hand side, you have a bunch of data, which are these like A, B, C, and D, and E's, and then you have these nodes representing operations. The moment A and B are, A, B, and C are available, the ordering you run these sets of additions and subtractions is not actually defined. There's like no strong opinion semantically from the executor about how to do this. And this is really fascinating because the fact that it's still data flow is like something that usually maybe disappears at a certain point, but throughout our entire stack, it still remains to be in this way. But, and why do we like having really, really rich data flow semantics at this level? Well, it's because these sort of graphs, by not having an opinion on serial ordering, exposes basically like the maximum amount of possible concurrency. Because in the previous example, we have no opinion of the ordering in which the plus and minus operators operate at. You can potentially run them concurrently and parallelly if you also have support for that. So this is really great because for some workloads like traditional AI, where you maybe like think about boosted trees, and certain pieces of hardware where you have like these CPUs with a lot of flexibly scheduled cores, you can basically guarantee this model to help you saturate like all of your hardware at once. For stuff like LLMs and GPUs, maybe it is less helpful. So that's the thing to call out. So that's the potential benefit. The cost you pay for this is that within the GraphRT, everything is basically asynchronous, right? So that just leads to essentially like a higher overhead cost for doing any sort of this executions. Furthermore, because there's no strong opinion at this stage about the order in which things execute, this can make some sort of optimizations like memory planning harder because you're not sure about certain lifetimes of buffers. They can be extended due to your uncertainty about when they're finished from being needed. So whether this actually hurts or not practically in the current state of the stack is unknown to me, actually. You should probably ask like Eric. He probably has a better opinion than I do. But I will say that like right now our utilization rates are so high. So this might be a future problem that we have to deal with. But right now it's not necessarily maybe the most pressing thing for some aspects of this stuff. Okay. And to round off the discussion here, I also need to like talk briefly about what MGP looks like. So here's what it looks like. Just remember, it's like data flow all the way down. It's buffer semantic. We also have this MEF stuff, which is just what we call the binary format the GraphRT expects. Again, MGP has really similar semantics to the GraphRT, so it's like a pretty one-to-one translation from my understanding of MGP to MEF. Okay, and then this set of slides is some other considerations that the runtime needs to do that Eric asked me to call out because I think they sound really important. So the problem of buffer management is actually like quite complicated in our stack because we potentially have to interface with like third-party tensors like PyTorch support. And that's interesting because then we have to manage a buffer we don't own. We might have to manage things like views. And the graph runtime or the runtime layer of the stack basically deals with all of this stuff, along with like things like memory planning and being fancy with allocating memory. So you're not like losing time on that. Finally, this part of the stack is also responsible for actually executing things, right? So that means they also have to deal with heterogeneous hardware. And so my understanding is they just like kind of use these device context and driver API libraries, but they also have to add support for like some of the concurrency primitives you see in GPUs, like streams, right? And then Mojo kind of handles some of the heterogeneity too, because it does that sort of split compilation of binaries. Okay, so that kind of concludes my overview of the tech stack. We covered a lot. This is sort of a high-level summary, and here's where we are within the entire stack, right? What we've done here is labeled maybe how future parts of the Tech Talk stack use the graph compiler. But thanks for coming, guys. Any questions?
I have a question.
Yes, Fabio.
So first of all, there is a lot of layout management that you do in your compilation. Do you need anything of the layout algebra that we have implemented for the kernels, where we do pretty much the same kind of operations? And can we share code? Can we ship? Is there anything we can contribute to each other?
Yeah. So I need to maybe refresh my understanding of the layout algebra. What I will say is that one key assumption right now in the graph compiler is that the inputs to kernels and the outputs from kernels, they're all contiguous. So my understanding of the layout algebra is it lets you like represent these like potentially non-contiguous things a lot more easily. Maybe when we...
Well, non-continuous is that there are strides.
Yeah.
Like say you want to split things, like you have a strided convolution, right? You have each piece of the strided convolution is generating a piece of data, and then they all end up in the same tensor. You can open windows on the output tensor and fill them independently. So that is something that helps. But what is really interesting in the layout algebra is that you can compose layouts and make sure that a compiler time you're not making mistakes. Like you can make it impossible to generate wrong memory access, basically.
Mm-hmm.
I don't know if that is a use case you actually need.
Yeah.
Or predicting what is the output layout after a bunch of transformations, right? You transform. What layout do I have at the end?
Yeah.
We can generate something like that. The other question I have is, okay, we have this data flow structure for the runtime, and of course it goes completely against what the GPU likes.
Yeah.
And we are not using anything of this data flow. And also, when you run things on the CPU, data flow may seem to help, but it actually does a really bad job at thread affinity with caches and memory and stuff like that. And so even if I were to run a sophisticated kernel on the CPU, I would probably prefer to use just the same approach we have with the GPU, where I have a bunch of threads. Each one has got its own name, like an identity, and there's its own piece of memory in the cache that it's precious. How do we have a uniform programming paradigm that maintains all these things?
Yeah, that's a really great question, Fabio. And the way I will say it is that even though the GraphRT is inherently like this asynchronous stuff, and you'll have to deal with the overheads from that, you can still arbitrarily chain things in order to have like a static execution order. Or you could, for example, imagine the unit of execution for the GraphRT as a kernel. You can make that kernel do a bunch of statically scheduled things, right?
Yeah.
So there's lots of strategies at this layer. I don't think it's a problem for runtime, but it's about how we then expose it progressively up to the stack and eventually give users control, maybe in the Graph API if that's what we need, right? So that's what I would say is the challenge is. I don't think like performance is never going to be an issue, but it's about like how you expose that control. That would be my main take on that.
I think my last question now would be, where are we with static memory planning?
Static memory planning. Is Nachi here? Since he's the one who worked on it.
Yeah, I'm here. We had a old static memory planning pass that was pretty buggy, and I think it would use like it would allow you to do memory planning on dynamic values as long as there were like factors of a single variable, like static factors of a single variable. Right now with static memory planning, we don't have anything right now. We have some like really basic buffer reuse for like identical sizes, even if there are multiple variables involved in the dynamic values. But yeah, we don't really have any real static memory planning at the moment.
Is there a plan to go back to a static memory planning?
I don't think so. I mean, I think the other thing is that like a lot of the buffers that are allocated within kernels. So which the graph compiler has no visibility of right now. So even if we did fully static memory planning, we would still see a lot of allocation traffic due to scratch memory buffers allocated by kernels.
Okay. And did you ever profile this kind of stuff and see if there was any advantage? I mean, any bottlenecks due to all these allocations?
Yeah, I mean, we've done like analysis of the traces, and like I mean, you can look at the GPU utilization, for example, like the overhead is not really an issue anymore. I mean, there's like a couple like microseconds at the very beginning before kernels are all queued up, but very quickly it fills kind of the word queue. So yeah, I haven't noticed it being an issue, but I think definitely that's something we want to work on in the future, is having a more robust memory planning system.
Cool. Thank you, guys.
Thank you, Fabio, for your questions.
Any other questions? All right, I think we can wrap up. Thanks, Andrew. That was a great talk.
Thanks,
We'll see
guys.
everybody next week. I think Kyle's going to talk to us about the pipelines layer.